lectures. So complex analysis is a beautiful subject. It's an incredibly powerful subject. And so the goal of today is to show you how using tools from complex analysis we can solve a variety of very difficult problems in probability with enormous ease. I am not going to rigorously prove every result from complex analysis, but I want to give you a flavor of why it's true. If you want to see the details, take Math372 next year or at some other time in the future. Even if you don't take those classes, going through these arguments will be a great way to review a lot of what you've done in earlier classes and see how all the math ties together and see why we've spent all this time doing this. All right, so let's do integration. So in one dimension, we have like the integral from a to b of f of x dx is f of b minus f of a. You know, the derivative of big F is little f, and the left-hand side is the area under the curve. So here's my curve, y equals f of x. Here's a, here's b. So why do we care about areas under curves? I'm sorry? It's probabilities. So we want to calculate stuff like this because it's probabilities. That's why we care so much about this. If we have an antiderivative, we have a closed form expression, these integrals are very easy. The simplest integral I can give you in one dimension, I won't, is the integral from a to a of f of x dx. It is so simple, I don't even need to tell you what the function is. What is the integral from a to a of f of x?
0.
0. Now, in one dimension, this is not that interesting. Where it's basically saying, I start here, I end here, and I want to see how much area is under the curve. In two dimension, however, it becomes interesting. I can take a walk. We'll see if the camera can actually track. Good. All right, so I can take a walk. Good. And I can come back to where I started in a non-trivial way. And so in two dimensions, geometry is more interesting. You can have closed curves that start and end at the same point, but you've actually gone somewhere, you've actually done something. So in one dimension, you know, this is a trivial statement. In two dimensions, asking what functions are there such that when you integrate them along a closed curve, you always get 0. That is a non-trivial task. And our goal today is to see which functions, I apologize for people who are sleeping, is to see which functions will have an integral of 0. Okay? We've already seen some hint with Green's theorem. And that basically relates, you know, the integral of f dz to, you know, a certain double integral, which is 0 if f is complex differentiable. And so, if we have a function that's complex differentiable, a lot of these integrals are going to be 0. The whole point in complex analysis is to find those few functions that are not complex differentiable, that blow up at a point in a nice way. And everything is going to come from that. So, if we have over here functions and derivatives, I'll do everything for Calc 1. We can change the letters. Derivative of x squared. Gotta be faster, guys. 2x. Derivative of x. Derivative of 1. Derivative of 0. Right. Derivative of 1 over x. Negative 1 over x squared. Derivative of 1 over x squared. Alright, we'll work on those drills later. Alright. What's missing on the right-hand side? What's missing?
1 over x.
There's no 1 over x. We have something that's degree 1 in x, degree 0 in x. We have 2 zeros over here. We don't have any, you can view both of these as the constant. You're going from 1 to 1 over x, there's no need to have the 0, that's fine. Let's just try and find possibilities. We're missing the 1 over x. Is there any way to get a 1 over x? So if we put in a log of x, we get a 1 over x. And now, x to the first power, x to the 0th power, x to the negative 1 power, x to the negative. Now everything proceeds correctly. This is the secret in complex analysis. It all comes down to dealing with the logarithm function and the function of 1 over x. So let's consider the following. I want to integrate along the circle z has radius r the function z to the n dz. So z is r e to the I theta. And actually, since I'm doing a circle of radius r about the origin, it's going to look like this. Well, if I'm going along a circle of radius r, this is the same as I integrate theta goes from 0 to 2 pi. Z to the n is going to be r to the n, e to the I theta to the n. And then dz, well, it's going to be r e to the I theta, I d theta. The reason is r is not changing. The only thing that's changing as I stay on the unit circle is theta. So I get r e to the I theta, I d theta. Right? I can pull out a lot of things. I have an r to the n plus 1. I can pull out an I. And I have an integral, theta goes from 0 to 2 pi of e to the I n plus 1 theta d theta. This is the same, using the Euler formula, as the integral theta goes from 0 to 2 pi of cosine n plus 1 theta plus I sine n plus 1 of theta. What is the integral from 0 to 2 pi of cosine of n plus 1 theta? So what would I get if I integrate cosine 2 theta from 0 to 2 pi? Cosine theta from 0 to 2 pi?
0.
I get 0. Is there ever a case when I don't get 0? There's one case you've got to be careful about. And there's a hint as to what that case is on this board here. What's the case I have to be careful about?
N equals negative 1.
If n equals negative 1, I'm integrating the cosine of 0 theta. What's the cosine of 0? It's identically 1. So if n equals negative 1, we get 1, else the integral is 0. Over here, if n equals negative 1, well then I identically get 0, that's no problem. And if n is not negative 1, I still get 0. So this integral turns out to be 0 unless n equals negative 1. If n equals negative 1, we're integrating the function 1 from 0 to 2 pi, we get 2 pi. The beautiful thing is, if n is negative 1, r to the n plus 1, well that's just the same as r to the 0, so the radius doesn't matter. And so what we get is that this integral is equal to 2 pi I if n equals negative 1 and 0 otherwise. This is the key integral in complex analysis. If I integrate the function z to the n, where n is an integer, along a circle of radius r, it doesn't matter what that radius is. The only time I get a contribution is if n equals negative 1. If I have the 1 over z term. Basically, it's the 1 over x term here. It's the only term that doesn't have a nice antiderivative. I'm sorry, that doesn't have. Yeah, that doesn't have a nice antiderivative because I'm going in this direction. All these functions have nice derivatives. The log function is not a nice function. People normally don't like to have a 2 pi there. They write a 1 over here, and they put a 2 pi I over here. And so 1 over 2 pi I times the integral of z to the n is equal to 1 if n is minus 1 and 0 otherwise. You can see this with the cosines and the sines. This is the key integral in complex analysis. So what it's saying is if I have a function, all that matters is the negative 1 term. So what I'm going to do now is I'm not going to worry about rigorously justifying all the statements. You would need to use some results about sequences and series. What class would you do that in? Real. So, for the sake of argument, I will assume you've all gotten A's in real analysis in the last 5 minutes. It was impressive. The fastest ever done in the history of Williams College. I'll see about giving you guys credit for that and fulfilling distribution requirements. Okay? Assume all series operations. Okay. or just major in physics or economics. Either one is fine, okay? We will assume we can do whatever we want. Let's say I give you a function f of z is the sum n goes from minus n to infinity of a n z to the n. Maybe n is negative 341. I just need n to be a finite number. I don't want to go off to infinity. I want to integrate 1 over 2 pi I f of z dz over a circle of radius r. This is the same as 1 over 2 pi I, the integral over a circle of radius r, the sum, n goes from minus n to infinity, of a n z to the n dz. What do you want to do? Switch. Okay? Good. You've all taken real analysis. You've all been able to justify this. Excellent. So now we have a sum, n goes from minus n to infinity, a sub n, then 1 over 2 pi I, the integral, absolute value of z equals r, z to the n dz. What does this integral equal? It equals that. It's 1 if n is negative 1 and 0 otherwise. The only term that survives is the a negative 1 term. So if I integrate any complex function that only blows up in one place, about a circle about the point where it blows up, all that matters is the negative 1 term in the generalized Taylor series expansion. We have converted integration to algebra, to finding just one term in the Taylor series expansion. The other things don't matter. Okay? If the function is well behaved, if it never blows up, there is no negative 1 term. N starts off at 0 or 1 or 2 or 3, and then the integral will be 0. So if f doesn't have any blow-ups, it will integrate to 0. So now, let's generalize. So let's say we have a nice region. F never blows up. And I want to integrate f along this region. So I want the integral of f of z dz. We evaluated that integral last time. We used Green's theorem. And by Green's theorem, what was this equal to? So it's Green's theorem and the Cauchy-Riemann equations. What does this all equal? So what do we show this integral equals? It's a double integral, and then when we put in the Cauchy-Riemann equations, what does that double integral equal? It equals 0. So if you have a function that does not blow up in the region, and you integrate along the boundary, it does not matter what the curve looks like. It's 0. This is the power of Green's theorem. I should have brought it down. I have it in my office. It was a prop I made when I was a grad student. I took a plastic bag and I taped it to a coat hanger. And what I did is, I would reach in and I would shift the plastic bag on the top. And I would not change the boundary of the surface. It would still be that coat hanger. And by Stokes' theorem, if I wanted to do the surface integral, those were equivalent to an integral over the boundary. All those integrals were the same. That's the power of Stokes' theorem. Here, what's nice is, for regions like this, as long as the curl of my function is 0, which in complex analysis means if you're complex differentiable, Cauchy-Riemann equations are true, the curl is 0, the integrals vanish. We can now integrate any function that doesn't blow up. If all you do is get 0, life is not interesting. You need to be able to get something else. And so what we're going to do now is we're going to consider a function that blows up in several places. And so this argument here is going to be generalized a little bit. So how many of you have seen Green's theorem before? If you are math majors, especially if you're thinking of going off to grad school, you need to learn Green's theorem. This will be on the GRE exams. Right. If you haven't seen it before, imagine now I have a function that blows up at 3 places. I can't just use this result because my function is not well behaved. So what we're going to do, I want to see if any of you have seen this in Green's theorem, is we're going to draw little circles going almost all the way around each of these points. And then what we're going to do is we're going to make little slits like this. And so now I'm going to come around like this. I'm going to come down this line, go around this circle, come back, continue going along, come down here, come back, go around, come up, go around, come back. And now in this region, the function f does not vanish, so does not blow up. So the integral over this outside curve is now equal to 0. Yes?
How do you define that function though? Doesn't that be really hard?
No, I'm not defining the function. The function is not changed. I'm changing the path of integration. So what I'm doing is I'm drawing a very small circle of radius epsilon about each point where the function blows up. Yeah, we'll assume there's only finitely many points where it blows up. And now I draw these little circles around it, and I draw these little slits going to and back. And in fact, what you could even do to make life a little bit easier is go completely around the circle and go along this line in 2 different directions. Well, if I go through the line in 2 different directions, the contribution of the integral over those lines is just 0, because I've gone in 2 different directions. So what we can do is we'll call this C1 for circle 1, C2 for circle 2, C3 for circle 3, and gamma for the original curve. We get the integral of f along the curve gamma. We always integrate counterclockwise. These circles are all traveled clockwise, so they're all going in the other direction. After you do the algebra, I don't want to spend all the time doing this. You get it's the same as integrating f over the 3 circles. Is that you can replace integrating your function over the whole region with integrating the function over circles about the points where it blows up. Again, this is complex analysis in 2 days. We are going at warp speed here. But the idea is to see that this is reasonable, that this is following from Green's theorem, that if I know how to integrate over circles, and if I know the integral is 0 in a region where the function never blows up, I can pass from the region I want to integrate over to the region I need to integrate over. Or in other ways, I can go from the region I need to integrate over to the region I want to integrate over. I can convert all integration to integrating circles. I can integrate over circles. That's the result we just erased. And so what you get is that, let's say this is a circle centered at the point Z1, this is a circle centered at the point Z2, this is a circle centered at Z3. I don't have a 1 over 2 pi I here, so I get 2 pi I times the residue of my function at Z1 plus the residue of my function at Z2 plus the residue of my function at Z3. One other way of writing this is it's 2 pi I, the a -1 coordinate of the Taylor series at Z1 plus the a -1 coordinate at Z2 plus the a -1 coordinate at Z3. We have converted integration to finding Taylor coefficients at 3 points. Okay? So again, blitzkrieg introduction. The idea is integration is hard. Algebra is easy. I'm going to try to show you right now how easy it is. Coincidentally, this happens to be already on the board. What a wonderful world. Okay? So this is the problem you were supposed to be thinking about. I cheated, I Googled it. This is the integral of a Cauchy plus a Cauchy is a Cauchy. So we start off with Lagrange's identity, a squared plus b squared is c squared plus d squared is the following sum of 2 squares. The reason this identity holds is complex analysis. The norm of a number z is x plus iy. If you square it, you get x squared plus y squared. The norm is x plus iy times x minus iy, the complex conjugate. If I take 2 complex numbers and multiply them, the norm squared of the product is the product of the norm squares. And this is where you're going to get now the sum of the squares coming from. So even though what I'm showing you entirely avoids complex analysis, it is relying on an identity coming from complex analysis. The point of this calculation, and I'm going to give you the link where I stole this from, is to show you that you do not want to have to think about this. This is possible to do using just real analysis, using just Calc 1. I actually just talked to one of the Calc 1 professors here about having her do this next year with her students. She was not too enthused. Just because you can do it with Calc 1 techniques does not mean that you want to do this with Calc 1 techniques. You have to be clever multiple times. One of the points of the big theorems is to reduce something to a situation where you no longer need to be clever. If I give you a quadratic and ask you for the roots, can you do that? Yes. How would you do it? In an emergency. Quadratic formula. If I give you a nice polynomial, you'll look at it and you'll try to factor in your head. If I give you x squared minus 5x plus 6, well, let's see, I can do 6 as 6 and 1, 3 and 2. 3 and 2, that's wrong. It'll be x minus 3, x minus 2. If I give you something nice, you'll try to just do it by looking. But if that fails, you have a black box method you can resort to. You can just go through the calculations. Here we had to be clever. So the first thing is, here's the Cauchy convolution. I'm dropping the 1 over pi squared to save time. We'll put it back later. 1 over 1 plus t squared, 1 plus x minus t squared. We need to evaluate this integral to get the Cauchy density. We use this product of sums of squares identity to reduce it to the following sum of two squares. The trick is we can write 1 as 1 squared, and we do have a sum of squares. And this is why in the definition of the Cauchy, we actually have it as a squared plus x squared. We're really thinking about using something like this. We now do a change of variables that u equal t plus x over 2. When you do that down here, you get 1 plus x squared over 4 minus u squared squared plus 4u squared. If you look at this as an integral in u, if I go from 0 to infinity, and I double that, that's the same as going from minus infinity to infinity. And the reason is, it doesn't matter if I put in u and negative u, it's the same value. So I can go from 0 to infinity and I can double. And I'm going to let m be 1 plus x squared over 4, because that doesn't change with my integration. I'm integrating with respect to u. This looks like a nightmare. I've got a u squared, I now have a u to the 4th term. The great change of variable is to let w equal x minus m over x. When you plug that in here, you get the following nasty integral, a w over square root of a w squared, but this is an odd function. And when we integrate over a symmetric region of an odd function, you get 0. You're left with the integral of 1 over 4 plus u squared. Well, by changing variables, we replace u with 2u, we get 4 plus 4u squared, we pull out the 4. That's now the standard arctangent. We can evaluate this. This is pi over 4m. We substitute in for what m is. We put in the 1 over pi squareds, and boom, there we go. Cauchy plus Cauchy is Cauchy. And the way it works is you get a 2 squared. And if you had Cauchys with 2 squared and 3 squared, you'd end up getting something very similar here, which I will leave as an exercise. This is doable using real analysis. You had to be clever multiple times. You had to think of using the Lagrange identity. You then had to, this change of variable is not horrible, this one's not horrible, this one is very clever. Thinking to do something like that and flip it. There's a lot of work here. What I want to do now is I want to show how this follows the Cauchy and Cauchy by just doing complex analysis. By using our result here, that the integral of f over a curve is the same as the sum of the integral of f on circles about the points where it blows up. So we're going to convert integration over hard regions to integration over simple regions. Okay. So again, I'm trying to justify why you want to take complex analysis. I'm trying to justify why you want to do all this stuff. This is hard. The complex analysis here is absolutely wonderful. So now, Cauchy plus Cauchy. So we have the integral from minus infinity to infinity, 1 over pi squared, 1 over 1 plus t squared, 1 over 1 plus t minus, x minus t squared. Okay. I'm going to write this a little bit. It's 1 over pi squared, integrate minus infinity to infinity, 1 over t squared plus 1, 1 over t minus x squared plus 1 dt. When does t squared plus 1 equal 0?
When t equals I.
At I and minus I. So this is the integral from minus infinity to infinity, 1 over pi squared, 1 over t plus I, t minus I, and then over here we have t plus x plus I, no, sorry, t minus x plus I, and then I think t minus x plus I. Okay, so it blows up at I minus I, x plus I, and x minus I. It blows up in 4 places. The integral we're doing is we're going from minus infinity to infinity. So the way we normally do this is we go from minus r to r, and then we let r go to infinity. Our function decays very nicely. We're integrating with respect to t. When t is really large, it looks like 1 over t to the 4th. So the contribution from very large t is negligible. What we're going to do is we're going to look at the following path. We go from minus r to r, then we go in this huge circle of radius r. Okay? What's the length of this circular arc?
2 pi r
Almost.
or pi d.
So a better way of saying it, because you don't really care about what the constant is, it's something times r. The length of this arc is of order r. Length of order r. I believe it's pi r, I don't care. It's something of order r. If you look at our integrand, if we now replace t with a complex variable z, we're going to be integrating the function 1 over pi squared, 1 plus z squared, 1 plus x minus z squared dz, going over our curve. When z is large in absolute value, this piece here is essentially of size r squared in absolute value. It might be a little bit less because maybe there's some cancellation here, but it's roughly going to be of size r squared. Worst case, it's going to be r squared minus 1. Similarly over here, the worst case is this is probably going to be r minus x squared minus 1. The denominator is going to look on the order of r to the 4th. The length of the arc is only of size r. So I have a function that's of size roughly 1 over r to the 4th. I integrate it over a curve of length r. What's the maximum contribution to the integral? I'm integrating something of size 1 over r to the 4th over a path of size r. What's the contribution? So on the top, what's my contribution going to be? So top, you integrate approximately 1 over r to the 4th over length r. So what does it contribute? Contributes approximately how much? So you've got something of size 1 over r to the 4th over a curve of length r. What will the contribution be? You're shaking your head, so you're on the spot now.
Me?
Yeah.
R or
Well, it's how long is the curve?
R.
And how large is the function?
1 over r cubed.
1 over r cubed, right? The function is at most roughly 1 over r to the 4th at each point, and I'm integrating it over a curve of size r. So the contribution is going to be on the order of 1 over r cubed. As r goes to infinity, do I need to worry about the contribution from the upper arc? No. So the integral of this function over this whole curve as r goes to infinity is going to just be the integral we want. And now from the big theme over here in complex analysis, all I need to do is figure out where the function blows up inside the region of integration. Well, we were told that there are 4 points. There's the point I, there's the point minus I, there's the point x plus I, and there's the point x minus I. Which points do we have to care about?
One's in the top.
The ones in the top. So we need to know what happens at I and x plus I. So if we go over here and we look, when I plug in x equals I, oh, here's my Taylor series expansion. It's blowing up when t equals I, and then everything else is well behaved at I. So I've got I plus I plus I minus x, I plus I minus x. Everything is fine. So if I want the -1 coefficient in the Taylor series expansion, all I have to do is just say, I can just plug in the constant term. Because everything else is well behaved at I, the constant term is just going to be the value of that function at I. So we get that this integral is going to be 2 pi I, and now I evaluate when I put in I, so I've got a pi squared that I have to take outside. When I put in I get a 1 over 2I, and now over here, I have I minus x squared plus 1. 1 over, or x minus I squared plus 1. For the next piece, I now plug in x, now I plug in x plus I. So when I plug in x, one of these, this should be a minus sign there. When I plug in x minus I, that's the piece over here. Everything else is well behaved, and I get, when I put in x plus I, the x's cancel, and I get I plus I is 1 over 2I again. And now over here, I get 1 over x plus I squared plus 1. But as r goes to infinity, this goes to the integral we want. So as r goes to infinity, get our integral is the above. Here we go. That's the answer. Does this look like a Cauchy?
Like a little, because the 1 squared.
A little bit. You know, we've got x squared, which is good. The I here is going to cancel with that I. We're going to have a 1 over pi, which is good. That's what the normalization constant should be. So after you do algebra, it turns out this expression is 2 over pi 1 over 2 squared plus x squared after you just do the algebra. You just have to simplify this. Remember in high school they taught you rationalizing denominators and simplifying and all that stuff? Here's one of the few times you actually need that skill. You know, I want to get common denominators, I want to cross multiply, I want to simplify. You're going to see a lot of things will cancel. And at the end of the day, you should get, if we haven't done any algebra mistakes, 2 over pi 1 over 2 squared plus x squared. So this is the power of complex analysis. It converts extremely painful integration to trivial integration, to just finding the -1 terms in these things. If it was a little bit different, if I had this whole thing squared, so I had this to the -2 power, things would be a little bit harder to figure out what the coefficient is. Yeah, this is a very quick introduction, but what I want you to see here is what do we need to finish up the stuff in probability. There is a reason I'm not putting this stuff on the exam. Okay? But I want you to be aware of what's out there, and I want you to see how everything pieces together. We can deal with Cauchy plus Cauchy is Cauchy. That's an extremely important result. It tells us that the Cauchy is a stable distribution. How many stable distributions do we know? 2 others, the Gaussian and the Poisson. So a process that's shape does not change is extremely important. And this allows us to handle stuff like that. Okay. Any questions on this? What I want to do is I want to do one more integration. Because I want to try to give you a sense of why we need the different assumptions we do. It seems reasonable that if 2 densities have the same moments, they should be the same. You know, that would be a wonderful theorem to have. 2 distributions are the same if and only if they have the same moments. We saw things like that held for discrete random variables. Unfortunately, it does not hold for continuous random variables. And you can have 2 random variables that have the same moments but are not equal. And the reason is they have to have more than all their integral moments the same, they have to have non-integral moments the same as well. So we're going to look at the log normal distribution. Out of curiosity, how many of you have seen this in, say, a stats class, the log normal? So few people have seen the log normal. One of the other reasons I wanted to do this lecture is it's a great way to introduce you to some other distributions we should see. The more distributions you have, the better chance you have of modeling something in the world. So we say x is log normal if the log of x is normal. Or u equals log x equals log x is normal, so x equals e to the u. Okay, so I want to find the density of x, given the density of the log of x is normal. How would I figure this out?
Use the CDF.
Use the CDF method. So again, we can use all this stuff to review a lot of the concepts we've done throughout the class. So CDF method. So we want to find the probability that x is less than equal to x. This is the same as the probability, x is the same as e to the u. Okay, well if e to the u is less than equal to x, what does that mean about u? It means the probability u less than equal to log of x. So this would be the cumulative distribution function of u evaluated at the log of x. We've got to be a little bit careful here. If x is negative, there's going to be a problem. I'm not going to worry about that right now. We'll assume x is positive. If x is negative, we're going to have to put in absolute value signs. So we'll assume x is greater than 0. Alright, so now, if I want to calculate, this is the cumulative distribution function of x, if I want to calculate its density, I just take the derivative of this at log of x, and now I need the derivative of log of x. What's wonderful about the CDF method is we never need to know the CDF of the normal distribution, which is good because there's no closed form expression for the CDF of the normal. We immediately take its derivative. So this is 1 over square root of 2 pi e to the negative, then it's argument squared over 2, so we get log squared of x divided by 2. Now what's the derivative of what's the derivative of log of x? 1 over x. We often write the 1 over x as 1 over x squared square root. Why would we do that? Because then we can bring that inside over here. And here is the log normal distribution. Alright. And so here, x will be greater than 0. We will not allow x to be less than 0 because we can't have such a probability. Alright, so here is the log normal distribution. This is, we'll call this density fx1. The log normal. And so the two densities we're going to have is we have fx1 of x, and we have fx2 of x is going to be fx1 of x, 1 plus sine of 2 pi log of x. So I've shown you a plot of this before. This is a strange function here, but what's nice is sine is always between -1 and 1, so this expression here is never negative. So it passes that test. To show that it integrates to 1 is a lot more work. I'm not going to bother doing that now. But it does integrate to 1. I want to calculate the moments of these two distributions and show you that the moments are the same. Okay? And there's some nice tricks for this. So we want to calculate the expected value of x, the a plus ib. So normally when we calculate a moment, we calculate the second moment, the third moment, the nth moment. I am calculating a complex moment, the a plus ibth moment. Okay? Now if I want to calculate the nth moment, I can take b to be 0 and I can take a to be n. But I'm going to do a more general calculation. Why? I need the more general calculation, and this will allow me to review again several concepts throughout the semester. So again, you can always think about what we're doing as this is a quick review of all the different ideas we've been looking at in the semester, and making up for the fact that we haven't been as theoretically rigorous as some people wanted. Alright, so this is the same as the expected value of e to the u a plus ib. Why is that the case? Why is it the same as e to the u?
You're just subbing in.
Yeah, I'm just subbing in. what it means for x to be log normal is that the log of x is normal, so x is e to the u where u is normal. Why do I want to do this? The normal density is a lot more pleasant to work with. As bad as it is, it doesn't have horrible things like x's inside the denominator down there. It doesn't have logarithms in the exponent. So I now need to integrate from minus infinity to infinity 1 over square root of 2 pi e to the negative u squared over 2, I forgot to put it in a moment, e to the u a plus ib du. Alright, we need to calculate this quantity. The first thing is I'm going to multiply by 2 and divide by 2, so I can bring this inside and complete the square. And when I do that, I'm going to get the integral from minus infinity to infinity, 1 over square root of 2 pi, e to the negative 1/2 u. Now I have a minus here, I have a plus here, so it's a minus a plus ib squared. And now when I square that, I now have a u squared minus 2 with the 1/2 good, a plus ib, but now I get a plus a plus ib squared with a minus 1/2. Right? So what do we need to do? Just make sure I haven't made any algebra mistakes up to now. Good. I need to put in an e to the 1/2 a plus ib squared from completing the square. We can now pull this outside the integration, and we get e to the 1/2 a plus ib squared, integral minus infinity to infinity, e to the negative 1/2 u minus a plus ib squared du. If only b was 0. If b was 0, I could just shift u by a, and I would be done. And this would be the standard Gaussian integral, which we know how to do. Unfortunately, we have the b here. Well, fortunately, we just took a blitzkrieg course in complex analysis. We know how to do integration. So what are we doing? We want to integrate, instead of minus infinity, we'll go from minus r to r. Here's the function we want to integrate. And what I'm going to do is I'm going to make a path like this. And what I can do is I can regard the b as being involved with the u. And so I'm not going to go through all the details. I don't think you really want to see all the details. But does this function blow up? If I look at the function e to the negative 1/2, and I'll call it z minus a squared. Is this function ever blowing up? It has no poles. If I go along this line over here, then z is just a real number. Z can be my u. This is going to be the line y equals ib. So this is going to be all points of the form, the imagined part is ib. So if I come up over here, I'm actually getting the integral I want. Or I guess I think I want it as a minus. I'd have to go down, but okay. Sorry about that. I want to go down. So here's minus r, here's r. I need to go down. Okay, so now here is the line y equals minus ib. Because there are no poles of the function, the integral of the function over this whole curve is equal to what? 0. Then you just show that along these two vertical sides, the integration is extremely small. Okay, and then I'm not going to bother doing that. If I was going to do that, it would take just a little bit of time. These are not that bad. And now it means the integral over this is this plus the integral over this is 0. So that means the integral over this equals the negative of the integral over this. Well, the negative means I go in the opposite direction. What that tells us is this integral here is the same as if I shift and remove the b. So again, this is a really fast blitzkrieg proof, but it's e to the 1/2 a plus ib squared. Integral minus infinity to infinity, e to the negative 1/2 u squared du. When I have a square root of 2 pi. That's the standard Gaussian. So the whole point of complex analysis is this reduces to the standard Gaussian. And we get that it's equal to e to the 1/2 a plus ib squared. So we calculated the moment. In a first pass in a subject, you should never try to understand every line and every calculation. That's not the job. The job is to see what's out there, to get a general sense of what tools and techniques are needed. When you're trying to decide which classes to take, does this excite you? Do you want to see why this is true? If so, take complex analysis. Do you recoil in fright and horror from this? Hide it on your face right now so I don't see, because I like it, and just don't take complex analysis. Okay? But you want to get a sense of what do you need to make the subject rigorous. If you're going to go deep in stats, if you're going to go deep in probability, this is the stuff you need to make these calculations work. And I want you to be aware of what you need. I don't want you to be so aware that I'm shoving it down your throat every day of the semester, but towards the end of the semester when we have a little bit of time, it's worth exploring this. This was just F1, we've got to do F2 now. Fortunately, we can cheat and we can get F2 without any work. And the reason we can cheat is that if you look at F2, F2 is very closely related to F1. So we've got this extra sine of 2 pi log x. And now we're going to use sine of theta is e to the I theta minus e to the minus I theta over 2I. If you haven't seen this, you can derive this from all the stuff we did with e to the I theta. Just a bunch of algebra games. So the sine of 2 pi log x is e to the 2 pi log x with an I minus e to the minus I 2 pi log of x divided by 2I. Well, e to the log x is x, so we get x to the 2 pi I minus x to the minus 2 pi I over 2I. So when I'm trying to calculate what's going on here, this is going to provide a very small shift in trying to calculate the moments. You know, I was trying to calculate before the moment the expected value of x to the a plus ib. Well now, when I put in this term over here, that's just going to change b by increasing b by 2 pi from this and decreasing b by 2 pi for that, and give me now 3 terms. So you can actually get the moments from this for free from knowing the moments for the other one. And so at the end of the day, just to save time, we get the following wonderful expression. So we get moments of F1 are e to the 1/2 a plus ib squared. For F2, it's e to the 1/2 a plus ib squared. I do apologize for not memorizing this. I think you'll understand in a moment why. Plus I over 2 e to the a plus I b minus 2 pi squared divided by 2 minus e to the a plus I b plus 2 pi. You can see the two shifts. One is plus pi, one is minus pi. Squared over 2. Alright, there's the moments. And the interesting thing, if b equals 0, then we have an e to the a squared over 2 minus e to the a squared over 2. What do we get? We get 0. They'll have the same moments here if a is 0. So is that what I want? If b equals 0. So if b equals 0, and we're looking at real moments, things are going to become very nice. But what you'll see is that there'll be choices of b where these moments differ. So even though they have the same, if a is an integer, everything is fine, but for non-integral values of a, there will be differences between the two. Right. So this ends the blitzkrieg introduction to complex analysis. Right, so let's just quickly recap. We've seen where Green's theorem comes into play. We've seen all the stuff on sequences and series, the exponential function, the integrations. We've seen where 1 over x and the log of x, where that interplay continues. This is all used to get to this beautiful result. If I have a function that doesn't blow up, the integral of it over a closed curve is 0. We can then use that to replace integrating a function that blows up with integrating just over little circles. and then getting the information from those little circles to get it everywhere else. This is the power of complex analysis. It allows us to do calculations like this and get beautiful closed form expressions when we don't have antiderivatives. Okay? So as you've gone further in calculus and seen that Calc 2 is the subject of the great lie, they are not closed form solutions, they are not antiderivatives. Complex analysis is the answer. It gives you the closed form expressions you want. We will do something now more stat side. On Monday we will do method of least squares. Okay.